Zuel Fellow at the Institute of Photonics, ICFO, where she works under the supervision of Professor Levenstein to study quantum many-body systems for her master's thesis. Today she'll tell us about numerical simulation of quantum many-body systems.
Good evening, everyone. Thank you for the kind introduction. Can I share my screen?
Yes, please. I think you.
Okay. Is my screen visible?
Yes.
Okay. And I hope that I'm sufficiently audible as well.
Yes.
Okay. Firstly, I would like to thank the organizers for inviting me to the summer school. It is a great honor for me to present at the summer school because I attended the summer school myself in 2019, and it was a very enriching experience for me. Especially, I would like to thank Pani Gray sir for this because he has been really supportive in me pursuing quantum sciences in general. In fact, here I have some pictures from the QIQT summer school in 2019. At that time, it was an in-person event. Okay. Now I'd like to talk about the outline of my talk. The talk is structured as follows. First, I will give a brief overview about the tensor network basis to study many body systems. Then I will talk about the extended Bose-Hubbard model. After that, I'll talk about ultracold atoms in optical lattices from an experimental point of view in terms of quantum simulation. And after this, enough context would be set so that I can talk about what my master's thesis is about. Let's begin with, and in each slide, you'll find a blue box, which would be the takeaway point from each slide. So if you feel lost in between, just make sure that you grasp the takeaway point at least. Let's begin with a very simple question. What is the most basic thing that we can do with a Hamiltonian that is given to us? The most basic thing that we can do with this is to diagonalize it, get its eigenspectrum, and out of the eigenspectrum, the eigenvalue that corresponds to the smallest eigenvalue will give us the ground state of the system. If I tell you to diagonalize the matrix for a two-particle system, you can do it by hand. 4 particles, no problem at all. But as the number of particles scale, the Hamiltonian size increases. For n-particle system, we need 2n coefficients to represent the state effectively. And the matrix that we will need to diagonalize is something which we cannot do analytically. So whenever we cannot do something ourselves or analytically, we use computers or algorithms for it, whether it is finding what 2 plus 3 is or finding ground state of a many particle system. In general, many body systems are hard to solve exactly analytically, so we resort to numerical simulation methods. Numerical simulation has been employed to solve different problems in different fields of science, mathematics as well, for many decades. But in quantum physics especially, numerical simulation faces untackled issues for systems with strong correlations especially. But many body systems with strong correlations, they lead to exciting physics and exotic phenomena like high temperature superconductivity and fractional excitations, etc. Very recently, about less than 2 decades ago, tensor network methods have been explored to study quantum many-body systems, and they have shown great success in studying condensed matter physics, atomic physics, and quantum information sciences in general. They have a lot of potential to address many-body physics problems. I'll start with describing some tensor network basics. If we have a spin half particle, the state vector can be represented in its spin basis, in basis of spin up and spin down as follows. And here C1 and C2 are complex coefficients. If you arbitrarily want to store information about the coefficients C1 and C2, you can store it in a two-component vector. If there are no conventions to be followed, you can store this information either in a column vector or in a row vector. Now, if we have a system of two spin-half particles, the state vector can be written in the basis form as follows. Now we have four elements. If you want to store information about these coefficients, you can store it either as a four-component vector, or you can store it in a 2x2 matrix. It really depends on how you want to store that information. Similarly, if we have a system of n spins and one n spin half particles, it can be written in basis form as follows, and this coefficient C can either be an n order tensor or a 2n component vector, depending on how you store the information. The whole idea behind tensor networks is that an nth order tensor can be reshaped into a 2 to the power n component vector, and by means of various matrix manipulation and vector manipulation and a lot of linear algebra, you can change forms between different kinds of tensors. The basic tensor notation that is used for tensor networks is the Penrose notation, and in that, a simple dot is used to represent a scalar or a zeroth order tensor, and a dot with a single index represents a vector, which is a first order tensor, and so on. This represents a second order tensor, which is a matrix, and in general, a shape with n open indexes is an nth order tensor. Now I'll talk about matrix product states. If we take an nth order tensor and iteratively apply singular value decomposition, in the first step, if you apply singular value decomposition, you can decompose the nth order tensor into a tensor with one index and another tensor with n-1 index. And to represent the coefficients or the information stored in the nth order tensor, which is 2 to the power n elements, for this decomposition, you can represent the coefficients in 2 raised to power n-1 into 2 matrix. And if you repeat this process with the bigger block, you ultimately end up with a state which looks something like this, which consists of n open legs and a structure like this. Mathematically, it can be represented like this, and here, these are complex matrices. That's where the name matrix product state arises from. Mathematically, it can be shown that the 2 raised to power n coefficients that are stored in a nth order tensor, within this matrix product state, we only need n into d into x squared elements to effectively represent all the information. Here, d is the 2 into the spin you have plus 1, basically spin multiplicity, and x is the bond dimension, which we will not discuss over here. But the main idea is that if you increase the number of particles in the matrix product state, it scales polynomially with n, as opposed to general scaling of a quantum system, which scales exponentially. So the key point over here is that a matrix product state, or an MPS, efficiently represents a many-body system. Now MPS is an effective way of encoding a many-body system, especially for one-dimensional Hamiltonians. It is useful for gapped one-dimensional systems. A gapped one-dimensional system is one in which there are no degenerate states, and there is a lot of difference between the ground state and the excited state. There are theorems that prove that why the matrix product state captures the physics of one-dimensional gapped systems. It is given by the Hastings theorem and area law of entanglement. Like we represent a state vector, like we can encode a wave function onto the matrix product state, we can also encode the quantum mechanical operators and they can be encoded into the matrix product state, and they are known as matrix product operators. For example, in this figure, you can see this is a matrix product state. This is also a matrix product state. And if you remember that in Penrose notation, an entity with 2 index is a matrix. So over here, these are the matrix product operators, which are essentially matrices in quantum mechanics. And if we contract this tensor network structure, it will give us the physical value of the observable, which is this. MPS basically is an ansatz, and we can use it to work with 1D gapped Hamiltonians and calculate various observables, etc. After we have done the representation part, now the challenge is to find that which state is actually the ground state, because an MPS, it contains information about all the states of a system. For finding the ground state, we used a numerical method called density matrix renormalization group. There are several other numerical methods as well, which can be used to calculate the ground state properties, but this one is most effective for matrix product states. If you can recall, ground state is just the expectation value of the Hamiltonian, and it can be variationally found out as well. A Hamiltonian which has local terms can be effectively represented with matrix product operators. The DMRG method, it makes use of alternating least square method to optimally find the ground state. And it is proven to be accurate for all the matrix product state calculations and its contractions in general. You can not only find the ground state, but calculate other observables as well with this optimization technique. DMRG is nothing but a variational minimization routine. So in general, in nutshell, the whole point of this is that we have useful numerical tools to study low entanglement many-body systems with matrix product states, DMRG, TDVP and TEBD, which are other optimization techniques. Now let's bring physics into the picture. A lot of exotic physical phenomena arise from many-body systems. Like if you remember, the Nobel Prize last time was given for spin glass, and it is studied with a quantum many-body system. A lot of physical models in atomic molecular optical physics, condensed matter physics, and quantum physics can be studied with the basics of Hubbard models, the Bose-Hubbard model and the Fermi-Hubbard model. They are important models for studying quantum many-body systems. Let's take a look at the Bose-Hubbard model first. It is the simplest many-body system that can't be reduced to a single particle Hamiltonian. And it is described as follows. This term relates to the kinetic energy, and these are the bosonic and annihilation and creation operators. This is the repulsive contact interaction term. These are the bosonic number operators. This is the chemical potential, and this term is important for if you want to add or remove a particle from the Bose-Hubbard model. For the Bose-Hubbard model, in the ground state, 2 different quantum phases exist at t is equal to 0. These different phases, for different values of parameters of t and u, these phases exist as follows: the Mott insulator phase and the superfluid phase. These phases and the Bose-Hubbard model has been extensively studied in various interaction regimes using numerical methods like mean and some analytical methods as well, but it is not exactly solvable using analytical methods as well. There are several numerical methods, quantum Monte Carlo as well, which can be used to study the Bose-Hubbard model. But what is more exciting is and experimentally, it was only realized in 2002, which is very recent. Now, if we add more kinds of interactions to the Bose-Hubbard model, which we call the extended Bose-Hubbard model, it leads to a very different phase diagram. Adding just dipolar interaction between the bosons on the lattice, it leads to new phases called the Haldane insulator and density wave, which are relatively new phases and haven't been studied as extensively as other phases of the Bose-Hubbard model. The Haldane insulator and the density wave phase, they have been theoretically and numerically calculated very recently in 2004. In fact, this phase diagram is calculated with an MPS and the DMRG calculation. All these different phases are usually characterized by change in correlation functions. Different one-body and two-body correlation functions, they suddenly change their value for different parameters and help characterize the phase boundary for different phases. That is how we identify different phases in a system. Now you might wonder that why is this all even important? We are identifying new phases one after the other, but why is it even relevant? In year 1925, the Bose-Einstein condensate was theoretically predicted by Albert Einstein and Satyendranath Bose for the very first time, but only in 1995, which was 70 years later, was it experimentally first realized by Wyman and Corlin in 1995. And once it was experimentally realized, it gave a thrust to this field. It was experimentally realized with help of laser cooling techniques where atoms are cooled down by means of using momentum of light in counter-propagating directions. It is rather counterintuitive that how you can use light to cool down the atoms. But it turns out that laser cooling methods, they can cool down the atoms to the temperature of nanokelvin. Nanokelvin is much cooler than even the outer space, which is around 2 Kelvin. Once these techniques were started to develop, it opened a new field of ultracold atoms in optical lattices and led towards unification of condensed matter physics model and atomic, molecular, and optical physics. Ultracold atoms in optical lattices serve as a very useful tool for quantum simulation. They help you realize experimentally various condensed matter physics models, which are very relevant for studying quantum materials and understanding properties of a collective system of particles. They help control a quantum system and manipulate the interactions by means of changing electric fields and magnetic fields around the trapped ions in a lattice. It has wide applications to study high temperature superconductivity, trapped ion quantum computers, topological order, ultracold dipolar gases, and much more. Very recently, a supersolid phase was realized in a dipolar BCE in the Ferlino group at QIQT, Austria in 2019. A supersolid phase has been theorized for at least 1.5 decades, but it was experimentally realized very recently. It is a material whose atoms are crystallized yet flow without friction, which is rather counterintuitive. Basically, quantum simulation with ultracold atoms in optical lattices is an emerging field and helps study quantum many-body systems better. So not only numerical methods exist to study many-body system, but there are experimental tools as well. And with the increase in interest in quantum engineering as well, more and more controllable systems are possible, and more research efforts are being directed towards studying these systems effectively. Now I'll talk about, with enough context set, I'll talk about what I work on. As we saw in the extended Bose-Hubbard model, in my work, I study that what happens to the quantum many-body system if we add fermions one by one to the extended Bose-Hubbard model, where the bosons are already interacting via dipolar interactions. We include the terms of fermionic hopping and fermionic dipole interactions as well. In this, we treat fermions as an impurity in a bath of bosons. And I try to find parameter regimes where a stable polaron formation is possible in different phases. A polaron is a quasi-particle which forms a bound state. Then I try to characterize phase transitions for the system and study the entanglement structure. I as well use matrix product states and DMRG and also TDVP to study this system. This is a work in progress and I'm still in the process of writing it up, but this is a very preliminary result. We have identified a parameter regime of contact interactions between bosons and fermions for which the bound states of polaron form for different phases. And this work is in collaboration with an experimental group at ICFO itself, who are trying to realize a quantum many-body system of dipolar bosons, and they are trying to add fermionic impurities to them. So my work is to identify parameter regimes so that those parameters can be tuned experimentally to realize different phases. The future directions that pertain to exploring many-body physics are basically that there are several descendants of Bose-Hubbard model which need to be studied. You can add all kinds of interactions and study them even more. Then I'm also interested in studying quantum Monte Carlo and other numerical methods to solve many-body physics. Then there is also a very recently emerging field about from 5 years that is to study tensor network methods on quantum computers. These are some of the fields that I'm interested to look in the near future. With that, I end my talk. Thank you.
Yes, there's a raised hand from Narendra Hegde.
Okay. Okay.
Yeah. Can you hear me?
Yeah, hi.
Yeah, hi. So thanks for the great talk. And if I understand correctly, this tensor network method, what you discussed earlier, basically requires that Hamiltonian has to be local and they obey the area law of entanglement. So could you comment
Yes.
on its interesting system where this method fails so that I think identifying these systems might lead to look into hard problems which can be solved using quantum simulation.
Okay, yes. So the thing is, at least for the matrix product state and DMRG, it works very well for, just a second, let me go to the slide. It works very well for 1D gapped Hamiltonians, which I presented, but there are various other tensor network structures like MERA or PEPS, projected entangled pair states, etc., which are effective or for different kinds of Hamiltonians, which might not have a local structure. But even then, as a thumb of rule, there are some Hamiltonians which might not follow the area law. And in general, it's difficult to solve them with tensor network methods because they follow the volume law. But it is possible to solve them with tensor networks, but not with matrix product state in general. Matrix product state is just an ansatz that works very well for 1D Hamiltonians, which are gapped. Does that answer your question?
Yeah, kind of. Yeah, thank you. Yeah.
See, Sabhyata, how do you compare, for example, DMRG with your method? Because DMRG also works very well in 1D.
Yes, DMRG, the optimization routine that I use is DMRG only. It is just that the encoding, the state encoding is done with matrix product state.
Okay.
If you encode the state in a different method and use DMRG, it might not be as accurate as if you use the encoding of matrix product state.
Okay. Thank you. Thank you.
I don't see any more questions in the chat box. Okay, thanks. Your talk was great. And
Thank you.
just one small question. So for it's probably not very relevant to the problem that you are solving, but for the kind of systems that you analyze, um, wouldn't QTIP be a good framework to look at?
I actually use QTIP to study entanglement dynamics of quantum many-body systems, but there are special well-written. You see that for any Hamiltonian, you need to create a matrix product operator, create a matrix product state, and there are well-written software libraries called TenPy and iTensor, which help you basically use those softwares to keep track of all the algorithms that you want to implement and kind of auto-generate matrix product operators. So
Okay.
they work well with the iTensor and TenPy, but QTIP is in general is good for any quantum mechanical system.
Okay. Okay. Thank you. So if there are no more questions, we'll move on to our next talk by Sowrabh Sudevan. Sowrabh, you're here?
Yeah, I am here. Can you hear me?
Yeah, I can hear you.
Okay. I'll.
Yeah, so Sowrabh, he's at ICFO Kolkata, and he's right now.
Yeah, I'm a student of Soren Das at ICFO Kolkata, and I will be. Can you hear me?
Yeah, I can hear you.
Okay. And I'll be presenting this work we have been doing over the last 1 year. So, yeah, I'm thankful to be presenting at this QIQT conference. I've attended it for the last 2-3 years. So, so here's the thing. So what we have worked on is constructing k-uniform qubit states. So let me start with the definition of what a k-uniform state is. So you take n qubit pure state with the property that every k-qubit reduced density matrix of these n qubit states is maximally mixed. Like if you trace away n minus k qubits from this, the resulting density matrix will be maximally mixed. So it's like you are trying to maximize the bipartite entanglement across all bipartitions. So, and now this is something that's easy to show, that if a state is k uniform, it is also 1 uniform, 2 uniform, up to k uniform. So it will include all the weaker properties if you have a k uniform. So now, why are we looking at these k uniform states? So one simple thing is that it's a generalization of Bell states in some sense. So like the Bell states, like in this example here, 0, 0 and 1, 1. So this has this property that if you take out any one qubit from this, it will become a proportional to identity, what you get. So it's a 1 uniform state. And this property is true for the 3 qubit GSZ state or even the generalized GSZ state. These are 1 uniform states. So a generalization of this idea could be to have larger subsystems which are proportional to identity and also across all possible such subsystems. So it could be a nice definition for multipartite entanglement. And here's an example for a 2 uniform state that we'll get to how we construct such more complex looking examples. So another justification for why we look at k-uniform states is that these have connections to quantum error correcting codes. Like this property of k-uniformity is connected to the distance in an error correcting code, but that's for another talk. I mean, that will be a whole thing. But yeah. So to understand these states, first we need to look at some basic ideas. So one thing is, if you have a general 2x2 density matrix, it can be expanded in terms of a sum of can be expanded in a basis of polymatrices. So for an n qubit system, you can expand it in a basis of tensor products of polymatrices. So that's what we've done here, equation 1. And now this is what we are going to be calling a block expansion. And these are the coefficients, the C, I1, I2, In. And each of these coefficients, the way you find them is by doing trace of rho times the matrix. So basically the coefficients are expectation values of those operators. Like you are expanding a state in terms of Hermitian matrices, which are these spin matrices, which actually correspond to certain physical quantities, and you are expanding a state in terms of expectation values of various physical quantities. So an example of that would be like this bell state, up, down, plus, down, up. You can expand it like this. You can write it as I, X. So here I, X, Y, Z, they are the X, Y, Z, they are the polymatrix X, Y, and Z. So, and similarly, this 3-qubit state can be expanded like this. So why do we do this expansion? So you'll see that in the next slide. So we've been able to show this nice little thing that for an n-qubit state to be K uniform, we need the expectation value of all block operators other than identity with weight less than or equal to K to be 0. So the weight of a block term is how many non-identity polymatrices exist in the term. Like in this case, IZX has 2 polymatrices in it. So this acts non-trivially on 2 qubits. So this is a 2-weight operator. Similarly, XXZ is a 3-weight operator. So what we are saying is if something is 1 uniform, it will not have any one-weight terms in it. One-weight terms are things which act on one particle. You can also call them, let's say, one-particle operators. So one particle operators, it might be interesting to note that they are like dipole moments, and 2-particle operators in this case are like quadrupole moments, and so on. So what you're saying is if something is 1 uniform, then the expectation value of all dipole moments is 0. 2 uniform means expectation value of all quadrupole moments is 0, and so on. So there's a nice physical thing. But yeah, when you expand the state in this basis, you can immediately see how much entanglement the state has based on the presence or absence of these operators. So now you can see that this state that we have expanded here, for example, it doesn't have any 1-particle operators in its expansion. You can immediately say that this is 1 entangled or 1 uniform. Now I won't go into the proof of this. It's actually a fairly simple proof. I can get back to this if needed at the end. So now the thing is, we are expanding states in this form of these block operators. So now there is a certain class of states for which this expansion has a very nice form. So the thing is, there are n-qubit states which, when you expand, will have exactly 2 to the power n terms in the block expansion with the coefficients plus or minus 1 by 2n. So, and also these terms they'll form a group, and all the elements commute with each other, and they all square to identity. They have all these constraints on them. So one example is I'm expanding, let's say, this state that I've written here. Now it's a 3-qubit state. It will have 8 terms in the expansion. These 8 matrices, you can check that they all commute and they all square to identity. Just because we are using polymatrices, they all square to identity. So what happens is they form this kind of group, set 2 to the power n group. So basically, this entire set of elements can be generated by taking 3 elements and doing all possible products between those 3 elements. You can get all the remaining elements. So now what is the use of this? So this is in some sense related to the previous talk, that this idea that a general state might have let's say 2 to the a general state of n qubits. If you want to store it in a computer, you would have to store like 2 to the power n numbers, right? But here, if it's a stabilizer state, it has this property that you need to store n operators, and each of those operators has length n. So you have to basically, it's like order of n square symbols, right? All the information in the state is compressed down to n square rather than 2 to the power n. Now, so this is a certain class of states which have this kind of possible compression in terms of how you can store it on a computer. But at the same time, we will show that this class of states has some interesting entanglement properties. So they're not uninteresting to study. So now the thing is, okay, so I have said that a class of like if there are n qubits, you will need n generators to produce all the terms in the expansion. So so these n generators have to have the property that they commute, right? So how do you, so there is a nice geometric way of writing down states such that they will end up commuting. So that is where graph states come in. So here basically you draw any graph, like a mathematical graph, which consists of vertices and edges, and there are connections between the vertices, and these are simple graphs. There are no self loops or any weights to the edges. So now what you do is you write down a set, the way you write down generators, like there is one generator corresponding to each vertex. So at this vertex, for example, there is a the generator will have the form like X acting on that site. I have numbered the vertices 1, 2, 3, 4, and there will be an X acting on that site, and a Z acting at the site which is connected to 1. Similarly, 2 is connected to 1, 3, and 4. So there will be Zs at all of those locations and an X at the location of 2. So this is now if you follow this recipe, you can see that this will give you a set of generators which commute, and they also square to identity. So obviously they will form a Z2 to the power n group, and then when you add them up, add up all the terms together, what you get is a stabilizer state. So you have a nice way of representing states by just drawing these graphs.
Sowrabh, can you elaborate? Can you just elaborate that example figure?
The figure. Yeah. Okay. So you have numbered these vertices as 1, 2, 3, 4, and there will be and you want to write down 4 generators. Like I'm claiming that this graph, this diagram here corresponds to a particular pure state. So the way you write down the pure state is like, and that pure state is a stabilizer state. So to construct a stabilizer state, you need to know the 4, like this is going to be a 4-qubit stabilizer state. So you need 4 generators to produce it, and there's 1 generator per vertex. So the generator at the first vertex is of the form, you will put an X as in there will be a sigma X acting at that site, at the first qubit site, and sigma Z wherever the first qubit is connected to.
Okay.
And similarly, 2 is connected to 1, 3, and 4, so it has Zs everywhere. 3 is only connected to 2, so it has a sigma Z at 2, and then X will be there at the site of that vertex itself. So this is how you get the 4 matrices. And these 4 matrices, you can see that they commute. I mean, you can show that they commute, and they commute, they square to identity, and so you can actually multiply all of them in all possible ways. Like there will be exactly 2 to the power 4 unique matrices you will get by doing all possible products between them, and you sum up all those 16 matrices, you will get a density matrix. That will be the density matrix of the pure state corresponding to this graph.
Okay, got it. Thanks. Yeah.
So now these things can be implemented in other ways also. Like the vertices can correspond to qubits prepared in the up plus down equal superposition, and the edges correspond to control Z gates. But for our purposes, this stabilizer structure is more important. So now, the generators of the block expansion come from the structure of the graph. Like I mentioned here, there is X, the generator for the ith vertex will be Xi times product over ZL, where L is all the neighbors of I as per this graph. So now the thing is, I have said that you take a set of generators and then you do all possible products between them, right? So by all possible products, it will be taking the individual matrices, and then it will be taking the product of any 2 matrices, any 2 different matrices, taking the product of any 3 matrices, taking the product of any 4 matrices, and so on. So an R product is a set of all products of R different generators belonging to a graph. So basically the full expansion will be the sum over all of these, like 1 product, 2 product, 3 product, 4 product, all of these you do. It actually comes like that: n choose 0, n choose 1, plus n choose 2, plus so on, will give you 2 to the power n. That's how it comes out to be. So to give an example, if there is a graph with generators these, then the 2 products will be these 6 matrices. So basically you're choosing 2 from this 4, 4 choose 2 is 6, so there will be 6 options. These are the 2 products. Now, this is another nice result that we have that, I mean, it's very simple to show that a product of R objects, like R generators of the graph, will give you something which has a weight more than or equal to R. Now, just using these two, we can come up with a bunch of graphs which correspond to various amounts of entanglement. So, so a block expansion, like I said, it will be sum over all the K products. And since as per the theorem 2, weight of an R product is greater than or equal to R. So the thing is, for something to be K uniform, it needs to have the property that it shouldn't have any terms which are 1 weight, 2 weight, up to K weight. And we know that K product will have minimum weight K. So to check if a graph has, let's say, K is K uniform, you need to check the weight of the 1 product, 2 product, up to K product. You don't need to construct the full expansion. Up to K product, then ensure that that has weight more than K, and then we are safe. Like the state will be K uniform. So this is the idea.
Sowrabh, can you please explain the concept of weight once more? How do you define weight?
Weight is, you can see these 4 operators here, right? X, Z, I, Z.
That's right.
So the first operator has a weight of 2.
These 4 are your generators, right?
The generators, yeah. Right. So the first generator here has a weight of 2 because it acts non-trivially on 2 qubits.
Okay. Got it.
That's it. So, so to check if something is K uniform, we need to ensure that the expansion does not have any terms with weight less than K. And we don't need to construct the full expansion. We only need to check the expansion terms till K products, because K plus 1 product will have a weight of at least K plus 1. So, so these 2 ideas we have to mix together to find a set of recipes. So now to get a 1 uniform state by this way of constructing states is very trivial. Basically, every vertex needs to be connected to just at least one other vertex, and then you will definitely get a 1 uniform state. Now what might be slightly interesting, like non-trivial, is the state here in diagram B. So this is a fully connected graph, and this also has exactly one uniform. So, and we can show why that is the case. So now to show that something is 1 uniform, the smallest weight block expansion term has to have a weight of at least 2 by theorem 1, and then by the other theorem we only need to consider the weight of 1 product. 1 product just means the individual operators. So if every vertex is connected to at least one other vertex, then each of those generators will have, like, there will be an X and there will be a Z somewhere else, because it's connected to at least one other thing. So it will definitely have a weight of greater than or equal to 2. So we are done. So now let's look at the fully connected graph. So a fully connected graph where every vertex is connected to every other vertex. So such a graph, like 2 generators will have the form, let's say a lot of Zs and then an Xi at some location, and then Zs everywhere else, and some other generator will have this form. Now if you multiply these 2 generators, what you will get is all identities, and then Yi, Yj, and remaining all the spaces will be identities. So you'll have something with weight 2. So it has a weight of 2, it cannot be 2 uniform, but that is the smallest operator there. So it is 1 uniform. So so this way of looking at entanglement, the GSZ state is not that interesting. I mean, it is only 1 uniform. So I'll get to that. Now a 2 uniform state. So any linear closed chain graph like this, so with n greater than or equal to 5 as in the number of qubits, is always 2 uniform. So you can show this. See, again, we need to check only the 1 products and the 2 products. Each generator has the form this Zi minus 1, Xi, Zi plus 1, because each thing is connected to the previous and the forward number. So Now this object has a weight of 3, so the one product is safe. It's more than 2, and one product has a weight of 3. Now we have to do the construct that multiply the two products. So you do a two product, and you can actually check for various numbers that it will always have a weight greater than or equal to 3. It actually has a weight of 4 actually. So it is quite safe. As long as you have more than at least 5 qubits in the system, you will, any two things you take out will be maximally mixed, any two. And for 3 uniform, the construction gets even more elaborate. You need to arrange, the thing is, there might exist constructions which are simpler, but we constructed these kind of things because it's easy to prove that this structure has this property. The way it works, the basic idea of the structure is that there will be 2 layers, and each layer, 2 layers of qubits, and each layer is fully connected with itself. And between layers there are parallel connections. So this can be, so the generators can be written in this kind of form. Hello? Okay. So the generators have, like you can write a certain matrix form. This is called an adjacency matrix in graph theory. But so you can see that generators can be written in this form. And so you can see that within, this is a block here which is full of, like, which is fully filled. Similarly for the 8 qubit example, there is a fully filled thing, and for the 10 qubit example, there's a fully filled block here and a fully filled block here, and there are off diagonal blocks which look like the identity matrices. Which so the idea is that, yeah, like I said, there are 2 fully, like you take an even number of qubits and then you split them into 2 halves which are fully connected, and there are parallel connections between them. Now the idea for showing that this kind of structure is 3 uniform rests in this property of these generators, that you need to check 1 product, 2 product, and 3 product, but there is a finite number of 1, 2, and 3 products you need to check. By symmetry, like for example, if you're looking at 2 products, you can take both things in the same layer, in which case you don't have to think of different examples, like, because it's fully connected within one layer. So you check the weight of one object, you have checked the weight of any such product. Similarly, if you have 2 things in different layers, they can be either parallel to each other like this 1 and 5, or they can be away from each other like 5 and 2. And those are the only 2 examples you have to check because of this nice structure for these graphs. So similarly, in this also you can show that these are 3 uniform by checking all the 1, 2, and 3 products. The symmetry makes it easy to actually count how many unique configurations there are in how you take these products. And the final thing we have is for a 4 uniform state. So a 4 uniform state comprises of, let's say, 25 qubits, like the smallest structure is 25 qubits. So the basic idea is that you need at least 5 qubits along each line axis, and they're all connected like this kind of a nice grid pattern, and with periodic boundary conditions. So this is like a torus basically. Now so the way this works is that, see, each of the 1 products have a weight of, which is the individual generators here. You can see they are connected to like 4 other points. So they have a weight of 5. So for a 4 uniform state, you want the smallest thing to be more than 4. You know, so here, yeah, fine, at least the generators are safe. And then you can show how, now this is a bit, there is a different way to approach this problem. So the idea is that when you try to reduce the weight of the product of multiple things, you can only make 2 different generators cancel at 2 different points because of the structure. So the smallest thing you can achieve with a product, but so if you take 2 things, like if you take 2 generators, like in figure B, 2 generators which are away by a lattice distance of 2, they will have the full weight, as in they will have 5 plus 5, they will have 10 weight. If you want to look for what is the smallest weight object, you have to bring them within 2 distance of each other, at which point you will only have up to 2 intersections. The way you can get more intersections is if there is a chain of these things which loop around, and so that is how we get the minimum size of the lattice and so on. So this is the work that we have been working on about K uniform states, and yeah, thank you. And these are the references. I can get back to some points if there are some doubts about. There's some question.
There is a raise.
I Sowrabh, absolutely amazing talk. So I'm actually, so essentially, I kind of feel like the states that you are writing, right? I can think of these states as Hamiltonians as well, because these are operators.
Hmm.
So, and like, just if you can go to the last picture from where you are moving out.
This one, okay.
Like this kind of, the loop thing that you just showed at figure D, it seems like your states, if I write it as a Hamiltonian, does it have some sort of topological properties?
So this is actually something that we are looking at right now. So this example, or we can even go a bit back. Let's say there is one property of these stabilizer states. Like I have, let's take some particular expansion. Like for example here, this expansion, right? So now if I write down a Hamiltonian which has these three terms, this xx, z, xyy, this, and put a negative sign in front.
In front of all of them, or just?
Yeah, in front of all of them, like minus xxz, minus xyy, minus yxz. The state in 2 is the ground state of this Hamiltonian.
Okay.
So yeah, this state is the ground state of a Hamiltonian. Like you can do that, and also, in fact, all of the eigenstates of that Hamiltonian have the same property of K, like whatever uniformity you can show for this, or whatever entanglement structure you can show for this, all of the states will have this property, all of the eigenstates of that Hamiltonian.
Okay.
So, and that is one thing. And when you talk about the topological property, this particular example, so this is actually something called like, if you write this in the Hamiltonian form, as in now I have drawn this graph to represent a state, but if instead I write down the Hamiltonian for which this is the ground state, that Hamiltonian is called a clusterizing Hamiltonian, and that has some interesting topological properties like symmetry protected topological states and so on.
I see.
And that topological property is connected to this. They talk about something called the degeneracy in the entanglement spectrum. So, so what we are actually looking for when we say that the reduced density matrix is proportional to identity is degeneracy in the entanglement spectrum, right? So these states are.
For me, it looked like you could have some sort of like loop operators as well, like the ones that you have in toric code, for example. Because I just got excited because the last picture that you showed in figure D, that looked like you had some sort of a loop going around, and maybe that corresponds to some sort of a loop operator.
Actually, what you said could be possible. We haven't thought about it that much. The last diagram for us was mostly about finding what is the smallest number of qubits which can host this state. As in this case, right? Let's go back to this loop. This object is 2 entangled if it has at least 5 qubits. But if it's 4 qubits and you draw a loop, it won't have this property of. So I keep saying 2 entangled, 2 uniform. It won't have this property. So there is a minimum size number of qubits you need. So we were trying to in the 2D torus type thing, we were that thing was to show what is that minimum size of that lattice we need, and we were trying to argue that it needs at least 5 cross 5.
Right.
So we need 25 qubits to get a 4 uniform state.
I see.
Okay, if there are no more questions, we will thank our speaker for his wonderful talk.
Thank you.
Thank you. We welcome our last speaker for this evening session, Dr. Siddharth Das from IIIT Hyderabad. He pursued his doctoral thesis in quantum information theory under Professor Mark Wild at Louisiana State University, and after a postdoctoral position at University with the questions. He has joined IIIT Hyderabad. So we look forward to, we welcome Dr. Das, and over to you, Dr. Das.
Yeah, thank you for the invitation. I don't know how overlapping my slides will be with your interest, because I didn't know much about the target audience. Now so please pardon if there is something that seems redundant. And also I would like to keep this interactive session. So if there is question at any point of time, please let me know. Okay. So I wanted to give, yeah.
Dr. Das, there is a bit of echo coming from your end.
Is it better or?
No, there's something that's vibrating as you speak.
Okay. Okay, how do I do that? Is it better now?
No, it's still the same actually.
Okay. Yes, big pardon. That may take some time. I just have one earphone. Can you give me, like, let's say 3 minutes?
Yeah, sure. Please take your time.
Okay.
We'll wait.